Okay, just an announcement to start with. The midterm is on the 19th of October. So that's a Tuesday and it'll be in class. I've sent the schedule of the next lecture, at least up until the midterm, to the TAs. We should be done with chapter 3 by then. So the midterm should include everything until chapter 3. So last lecture at the end we were looking at content delivery networks. So CDNs was one of the new technologies that came about in the late 90s to work around some of the problems with the internet and some of the problems with delivering high volumes of content to clients. Another new technology that came about in the late 90s is peer-to-peer networks. So the programming assignment that you have, once you're done programming with it, I'll advise you to start on it right away because it might take time. The programming assignment that you'll do will sort of teach you the principles of doing things at the application layer. So you assume the network is providing you some services, and using those services, what can you do at the application layer to improve performance, to provide new types of services. So CDNs operated almost completely at the application layer. They do nothing at the network layer or at the transport layer. Another technology that operated completely at the application layer is P2P networking. So P2P networking started with Napster in the late 90s, and then there were different architectures proposed. Napster had a particular architecture, GNU-Tella had a different architecture, Morpheus, which is the basis for Kazaa, has yet another architecture. These different architectures have different sort of identifying features. What kind of directories they hold, what kind of topology they have. And after sort of this initial wave of P2P architectures, there has been a lot of interest in P2P in the research community. So these architectures were proposed by systems people who built something and people started using them. And then the researchers sort of got into the act, tried to analyze it, and came up with different kinds of architectures, which we won't look at in this lecture. But once we've done, let's say, network layer, then I'll introduce these new P2P architectures, which are based on distributed hash tables, or DHTs. We'll take a look at that later. But today we'll wrap up the application layer by looking at the early P2P architectures. There's another new P2P system called BitTorrent. How many of you have heard of it or used it? So we'll also look at how BitTorrent works. That's also a very interesting system. So P2P file sharing, all of us know what P2P file sharing does. You run a client application on your computer. You're looking to download some object. It could be a song, it could be a movie or whatever. The P2P network that you connect to will let you search for that object, tell you where it is, and then it will let you download the object. So the programming assignment that we did is an example of that has been assigned, is an example of providing this kind of a network. The service that network right now offers is a chat service, but the service could as well be a file sharing service. Now, why are P2P systems so successful, or why are they used so heavily and why so many users are able to get reasonable performance out of P2P systems. The critical part here is this last line. In a P2P system, all the payers are also servers. So when you join a P2P system, when you're searching for a file, when you're trying to download a file, you have also offered your own set of files to the P2P system. So while you're downloading, you're also offering your machine, your bandwidth, your CPU to the other users in the network for download. So as more and more users join this network, the number of clients goes up, but the number of servers also grows up. So the number of servers grows with the number of clients, so it becomes very scalable. Of course, there are issues of freeloaders or free riders or selfish users who only download data but never offer. And there are ways to get around that by having some sort of repetition system or a priority system based on the number of downloads you have offered or the number of uploads you have done. But the critical aspect of peer-to-peer system is that it's very scalable. So now let's look at different kinds of architecture. So the original Napster design, where it all started, had two components to the architecture. See, what do P2P systems offer you? They offer you, if it's a file sharing system, a way to search for what you're looking in the network and then a way to download it. The search part of Napster was centralized. Napster had a centralized directory server where all the searches from these peers were going in. When you sent a query, this centralized directory server that Napster had would look through the current clients which were connected to this P2P system and would look through all the objects that those clients had offered. If there was a match, then the client which had requested that search was told about all the identities of the other clients who had that file. So the search part of it was centralized. All searches are going to this central server. But then the download part of it was peer-to-peer. You sent a query in, Napster told you where the file is, and once you knew where the file was, you had a direct connection to the other client to download the file. So the files themselves were never going through the central server. But the central server maintained a directory of who is currently connected and what files have they offered. So there were 4 steps to the Napster architecture. You connect to the Napster server. You upload your list of files that you are offering to the network. And then you give server keywords to search the full list with. So the files that you want to download, you're going to give to the server. The server will come back with a set of answers of nodes which have that particular file, and then your client program will choose the best of those correct answers depending on round trip times and download bandwidth. So in the first step, file list is uploaded to the central server. Then a user requests a search at the server. Napster will send back the results. The results will say that there are these 2 clients which have that file that you're looking for. Then the user will check which client is closer in terms of bandwidth. Bandwidth is decided roughly by round trip time. And then the user will select the best server and download the file directly. So the searching is happening in a centralized manner, but the download happens in a peer-to-peer manner. This is the functionality offered by the centralized directory server. It will collect the list of all files offered by all the peers that are connected at any point to the server. It will maintain connectivity information of the peers. So I connect to the server, I upload a list of files, I'll also send my IP address to the server, which is then relayed back to any client whose search I matched. The problems with this centralized directory system was that there's a single point of failure. If the central directory server goes down, then the architecture breaks down. You cannot search for anything, you cannot locate any content on the network, and the whole system breaks down. Secondly, it's not scalable. Even though the downloads are happening P2P, the search is still centralized. So as the number of clients goes up, the load at the server as far as search is concerned is going to go up. So there's a performance bottleneck there. And then there were issues with copyright infringement. Yeah.
Copyright infringement is not unique to the centralized model. Isn't the issue the fact that because of copyright infringement, this model is more easily shut down?
More easily shut down.
All these models are going to have the same copyright.
Right, but the completely distributed models, you don't know what to shut down, where to shut down. So copyright infringement, because everything is residing in this particular directory server, it's easy for RIA or MPAA to go to that server and shut it down. In a distributed system, not that I'm advocating it, it's much more difficult. So then we look at a decentralized directory. In a decentralized directory, this whole directory information is spread amongst all the participating peers. So now what this decentralized directory does is, it also makes the search functionality of the peer-to-peer network decentralized. So the searching load is also spread amongst all the peers, and hence the performance bottleneck is removed. There is no central server which is handling all the search queries. So as more clients join in, the search load on any particular server is not going to go up. Each client is providing not only the functionality of providing objects, but also providing search or search results. So these peers in a decentralized directory form an overlay network. I'll explain what an overlay network is. And even in the decentralized directory system, there are two kinds of topologies. Morpheus or Kazaa uses a hierarchical topology, whereas GNU-Tela uses a flat topology. So what is an overlay network? Well, an overlay network, an actual network consists of different kinds of N hosts connected to different routers, connected to different ISPs or autonomous systems that connect to each other. So this is what is commonly called an underlay network, or the physical network which connects all these N systems together. An overlay network, on the other hand, operates at the application layer. So now you look at only the N systems, you forget about the underlying network, you forget about the autonomous systems or the routers they're connected to, and you look at logical connection of nodes. So as an example, in this overlay network, this node here, which is, let's say, a server or some machine, is directly connected to this node here. There is a direct logical connection, and as far as the overlay network is concerned, there is a direct connection between these two nodes. If you look at the underlay network, at the physical network, this logical connection is going through one router, another autonomous system, two routers there, and then finally a third router. So the physical or the underlay connection is going through multiple hops, but as far as the overlay network is concerned, it's going directly. So in the overlay network, those two machines have the ability to talk to each other directly. in a virtual sense. So is the notion of the overlay network clear? Another thing is, in the overlay network, you have one thing is that these two machines have a direct logical connection, whereas these two machines, which are on the same physical network, same autonomous system, as far as the overlay network is concerned, they don't have a direct connection, because this machine does not know about this machine. So to get to this machine in the overlay network, the route that you might have to take is you go from here to here to here, 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 and somehow you have to reach here. There may not be a direct route in this overlay network. Actually, yeah, there are two overlay networks which are decoupled from each other. So two machines on the same physical network may not be neighbors of each other in the overlay network. They may not even know about each other in the overlay network. So overlay network works in these logical links. So if you have an overlay network, let's say you are running on Kazaa or Morpheus, that tells you that there are currently 5 million users logged in. So in that system, your node which is connected to Kazaa or the Morpheus network, does it know, is it connected to all the other users in the overlay network? If yes, or if no, why not? Yeah. So only the supernodes, only a small subset of nodes. Let's look at the Morpheus architecture. In the Morpheus or the Kazaa architecture, nodes with join and overlay are assigned to group leaders or the supernodes. And these group leaders themselves form a logical connection. So when you're a new node, if you're an ordinary pair, when you join the system, you get attached to a particular group leader or a supernode. And these supernodes are then talking to each other. And this overlay network is highly dynamic. Supernodes come and go, ordinary pairs come and go. The neighborhood system continuously changes. The flat overlay model, which is used by GNU-Tella, in that model all the pairs are equal. There is no notion of a supernode or a group leader. Nodes join the network by querying bootstrapping nodes. So a bootstrapping node will tell you the location of some nodes on the network, and you join this overlay network by connecting to these nodes whose location was returned to by the bootstrapping node or some sort of a directory service. So notice the difference between the GNU-Tella architecture and the Morpheus architecture. In the GNU-Tella architecture, each node is connected to a small number of neighboring nodes, which are pair nodes. In the Morpheus architecture, if you are an ordinary pair, in the overlay you are only connected to one supernode. And then the supernodes are connected to multiple different nodes. So if you're not a supernode, in Morpheus, you have only one neighbor, which is your supernode. Whereas in Gnutella, you have a small number of neighbors. Yeah.
I think Morpheus is switched to Phil the past 3 years.
I'm sorry?
Morpheus is switched to Phil the past 3 years. The only network using this system right now is Kazaa.
Well, Kazaa uses Morpheus underneath. Morpheus is the architecture. You're sure about that?
Quantico is called Fast Track, and Kazaa and Morpheus used to use them both.
So Morpheus has switched to.
Yeah, to Bluetooth because they want to pay the license fees, so they switched over there.
Okay. But Kazaa is still using the hierarchical architecture. Okay. The time to update my notes. So okay, model used by Kazaa. And how does Kazaa work? How does the searching work? Well, group leaders here act like the centralized server in Napster. So when you're a node, when you get attached to some group leader, you upload your list of files to the group leader. Group leader will maintain a directory of its own smaller group. And whenever you initiate a query, your query is handled by the group leader first in your local group, and then it is forwarded to other group leaders. That's the rough architecture of these hierarchical overlays. In Gnutella, on the other hand, you do the querying by flooding. So you search by flooding. So you initiate a query of a file that you want, and you send this query to 7 of your partners. If they don't have it, they are going to contact 7 of their own neighbors or partners, and there's a maximum hop count of 10 for this search. So TTL of 10. And the requests are simply flooded. There is no real tree structure. Once the files are located by this flooding, the answer is sent back to the querying node, and the final file transfer is done by a direct HTTP connection between peers. So again, the final transfer is going to happen directly between the peers. You're not going to use the route used to locate the content. This slide explains the basic query flooding architecture. The pros and cons of the query flooding architecture is that, well, the pros is it's completely decentralized. There is no notion of a super node or a centralized directory centralized directory server. No peer has to maintain any sort of directory info. Peers might cache some search results, but they're not going to store the directory info. The cons of Gnutella architecture is that the query traffic might be excessive. This flooding creates a lot of control traffic or query traffic. And the other problem with query flooding is, remember, you're going to forward a query 10 hops on the network. After 10 hops on the network, the query is going to stop, it's not going to propagate further. So if the object that you were looking for is not within 10 hops, then your P2P network will say that this file is not in the network. So you might miss out on content which is present in the network but is not within 10 hops of your node. And then the maintenance of this overlay network is also heavy in terms of control traffic. Decentralized directory again, the group leader is keeping track of the content of all its children, and queries are propagated to the group leader and then to other group leaders in this hierarchical overlay. So a problem with this architecture is also that some nodes have a heavier burden than the others, and depending on how the search is implemented, it will have the same problem as GNU-Tella, is that you might miss out on some content. The structure of this hierarchy is also, it does not permit you to locate all the content in the network, because if you have millions of users, you have to think of different levels of these group leaders, and also you can't imagine every group leader talking to every other group leader. It simply doesn't scale. So this technique also might miss out on some content in the peer-to-peer network. And the search time is also not fixed in either of these systems. In GNU-Tella, you cannot tell how long the search will take. The query has to propagate through the network. Each query might take a different amount of time. In this system, the query has to propagate from the group leader to other group leaders, and the time that the search takes is not bounded or constant. So later on in the course, we'll look at new architectures proposed for P2P systems, which are DHT based, distributed hash tables, in which the search time is O of 1. You can locate content on the network very fast. And the idea behind that is introduced in the programming assignment, is using hashing. So we'll look at those ideas in detail later, and that DHT based architectures also ensure that if there is content in the network, you will find it. You're not going to miss out on any search. So both GNU-Tella and Kazaa, or the fast track, they are decentralized systems, but they are not completely decentralized. Why not? Because bootstrap nodes are needed for both systems to identify or to locate nodes which are participating in this P2P or overlay system. But the load on the bootstrap node typically is not very high as compared to, let's say, a centralized search server. But still, you need the identity of a bootstrap node. And in the fast track architecture, the group leaders can get overloaded. So we'll look at how these problems are addressed later. BitTorrent works by splitting up what you want into different chunks, and BitTorrent is actually quite interesting. We'll look at it later in detail. While you're serving a file, yeah.
What's more efficient, the hierarchical overlay or the platform?
Efficient is hierarchical.
Is it faster as well?
Faster in what?
Searching or downloading? Downloading comes.
Downloading it doesn't matter, but searching hierarchical is faster. And it's also much more efficient in terms of the control traffic, the search traffic that you generate, because the search traffic is very directed. In flat, it's going to propagate across the network. A lot of needless queries are generated, and a lot of repeated queries are generated. So now we'll switch to the transport layer. So when we are talking of P2P systems or overlay networks, we are talking about communication that happens. This is stuck or what? Well, communications that happens between different processes that are running on different computers. So you might have on your computer a chat application running, a P2P application running, and you might have a web client. The crucial thing here is that on the communication in the application layer is happening between processes. It's not happening between nodes. So application layer is happening between processes. When we get to the network layer, we'll see that the network layer handles communications between nodes or end systems. So we need something that is going to bridge this gap. A network layer, the network layer, which are the nodes that you saw in the underlay network, the routers which provide the physical connectivity, they have no idea or no notion of the different applications that might be running on a given end system. They are simply going to transmit packets between end systems using some sort of routing mechanism and different kinds of link layer technologies. Application layer is talking process to process. So we need some sort of layer which will take this network layer communication and split it up into the right process. Right? When you get a packet from this node to this node, the network layer will take care of the delivery between the nodes. There has to be something else which will look at the packet that has arrived here and deliver it to the right process. Similarly, at this end, packets which are going from these different processes have to be delivered to the network layer. Again, the network layer will not know about the individual applications that are running, but it only knows that it's arriving from this host. So the main job of transport layer, one of the main jobs of this transport layer is to provide this multiplexing at this end and demultiplexing of packets at the receiving end. So at the sending end, the transport layer will take information from the application layer, multiplex it, and send it to the common network layer, which will take care of the delivery. And at the receiving end, when this end host receives this packet from the network layer, the transport layer will then demultiplex it to the right application. So one of the any transport layer protocol has to provide this multiplexing and demultiplexing of information between processes. The network layer will take care of the actual delivery. The other functionality that is provided by transport layer services is reliable data transfer, flow control, and congestion control. Now these may or may not be provided by any transport layer protocol. We'll see what are the principles behind reliable data transfer, flow control, and congestion control. Flow control is used, well, reliable data transfer is used to ensure that every packet or every bit of information that you wanted to send from an application reaches the other end. The network layer does not provide any guarantees of reliability. It might drop packets, it might make bits in the packet corrupt. It's providing no guarantees. The transport layer will have to provide somehow reliability built on whatever the network layer provides, and that's one of the jobs that TCP does on the internet. It takes a network layer which is unreliable, builds functionality within itself to make sure that every packet is reliably transferred. So that's the principle of reliability. Then TCP also does flow control and congestion control. Flow control ensures that the rate at which you're sending information from your end node is the rate which can be handled by the receiving node. So flow control does a rate matching between end systems. For example, your end system might be a PDA connected on a wireless dial-up or cellular link, which has, and the PDA has a slow processor, it doesn't have very fast memory. And the machine that's sending information to the PDA is some high-end server. So this machine is able to pump out traffic at a very high rate. It's maybe connected to a broadband connection. But the PDA won't be able to receive that information at the high rate at which this server can send data. So flow control will make sure that the rates of these two machines or applications that are talking to each other get matched. Congestion control, on the other hand, deals with the network which is connecting the two end systems. So the communication is happening through this network. And let's again look at the PDA and a cellular connection example. The rate mismatch for flow control dealt with the CPU and the processing capabilities of the end systems. The server was a high-end server with fast memory, fast CPU, so it was able to pump out information at a high rate. PDA, slow CPU, slow memory, it's not able to consume that information at a high rate. So flow control does this rate match. Congestion control does a rate matching of the network. Now our server is connected to a broadband connection. So the pipe here is very fast. It can generate data at a fast rate and it can also send data at a fast rate. Now a pipe here might be very slow. You might have a laptop connected to a dial-up cellular connection, and so this bandwidth is slow. Now the laptop, in terms of CPU and memory capabilities, might be able to match the rate at which the server is sending. But its connectivity to the network is not symmetric. So the rate at which you're pumping data into the network is not matched because of this asymmetry. So congestion control will make sure that the rate at which you send data to the network doesn't cause congestion in the network. So if you're sending data at a high rate here, and this link is a slow link, then congestion will happen at this link, queue will build up, you'll have packet drops, you'll have delays. And it could happen anywhere in the network. Any of these links here might be a low bandwidth link in the underlay network. The congestion control aspects make sure that the final rate at which you're transferring doesn't overwhelm the network. Yeah. No. Because flow control deals with the capabilities of the end system. See, you might have two powerful servers talking to each other. One server has a broadband connection. The other server is connected using a cellular wireless connection. So to maintain the right rate, you need congestion control. On the other hand, your PDA might be connected directly to LAN using an Ethernet connection. But it won't be able to consume information at the rate at which the server might send information. So let's say your PDA is connected to the LAN. Your LAN is 100 megabits per second LAN connection. There are only two machines, your PDA and a server. If you are sending information at 100 megabits per second, think about the PDA. How large is the typical memory of a PDA? 32 megabytes. So the network connection is able to sustain that information, but the PDA doesn't have enough buffer to absorb that information, process it, and consume it. So flow control is concerned with the end systems, congestion control is concerned with the network. So they are two different concepts, but TCP handles both. Is that distinction clear between flow control and congestion control? One is the end system, the other is the network. So let's look at how these transport services work. So the transport protocol will provide a logical communication between application processes running on different end hosts. The application are talking to each other directly. They're not really concerned about what's happening in the underlay network or in the physical network. They get a logical end-to-end transport connection, or it might be connectionless if it's UDP. The transport protocol that run in the end systems will break up the information that you're trying to send into segments or smaller chunks. These smaller chunks are then passed to the network layer. The network layer will route it through the physical network, and at the receiving end, the transport layer will then first reassemble these smaller chunks into messages and then pass it up to the application layer. So what are the two main transport layer protocols that exist on the internet? Well, TCP and UDP. TCP provides congestion control, flow control, reliability, and a notion of a connection setup. UDP is a very basic, you say, no-frills extension of the network layer. The only functionality that UDP provides over what the network layer or IP provides is multiplexing and demultiplexing. It does not do any kind of flow control, congestion control. It does some sort of reliability in UDP. UDP won't do reliable data transfer, but UDP has some functionality which tells you if there's something wrong. It's not going to correct it if something is wrong, but at least you have a way of knowing if something is wrong. So UDP is unreliable, but it can tell you if things have gone wrong. Neither TCP nor UDP provide any delay guarantees or any bandwidth guarantees. Yeah.
Can't you prioritize traffic and say that some traffic is of a higher priority than others?
Can't you prioritize traffic? So where do you want to prioritize traffic?
So if you own a router and you're sending control information to the router, you may want to give your control information to more than your traffic.
Right. So all routers have to agree that that control information is more important than the data that you're sending. So to implement priority, you have to implement that priority system through the entire network. If there's one link that does not respect your priority system or one router, then your entire chain breaks. So to implement a priority system, it has to be implemented at least in the network layer. You can't really implement it in the transport layer because it's not going to give you much. You implement something here, but when it passes through the network, if the network does not respect that, then you're dead. It doesn't matter. So there's been proposals, there have been different proposals to implement this kind of priority in the network layer, something called diff-serve or differentiated services. So later on when we get to the network layer, I'll talk about diff-serve and how that implements priority. Yeah.
But does TCP have any priority, let's say, for between applications on the whole system, in which one application is requesting a lot of data and other 5 applications requesting very little bit of data? So then it can prioritize which one that the smaller applications get more control so that they can end before the larger application runs and takes up all the time and the bandwidth. Do you have something like that in TCP? I mean, like one application requires 2 MB of data and the other 5 applications will just need to send or receive some KB of data. And suppose there is no mechanism to queue them correctly so that the 2 MB is just waiting and sending all the data and hogging all the bandwidth and the others are just waiting for it to complete. So does that happen in TCP?
So that kind of priority you don't implement with TCP because TCP is unaware of any other application running. TCP's job is just to provide a transport between one application and the other. It's not aware of the other applications that might be running here. So it's not doing TCP itself is not doing any sort of coordination. To implement that kind of priority, you have to go to the operating system. The operating system has to look at everything that's running and then do some sort of priority there. TCP is unaware of anything else. TCP is only concerned with one application with really one socket. It doesn't know of other sockets and it doesn't care. So let's look at multiplexing and demultiplexing. The demultiplexing at receive hosts. So when you send a packet from an application, let's say P3 running at host 1, the process has a socket associated with the transport layer connection, and that socket is going to talk to another socket on host 2, which is then connected to the application running on that host. So at the sending host, multiplexing involves gathering data from all these sockets and enveloping these data elements with a header, which will later be used for demultiplexing. At the receiving host, this receiving host, host 2, is receiving packets from different end hosts destined for different processes. So the demultiplexing involves collecting these packets from the network layer, link layer, and then at the transport layer it has to split these packets to the correct socket or to the correct process. So at the sending host you have to collect the packets and send them on a network layer. At the receiving host you have to collect packets and send them to the right socket or the right application. So how does demultiplexing work? Well, the network layer packet or the IP datagram has source IP address, destination IP address, and the transport layer segment. So the datagram is not going to contain anything beyond the source and the destination IP address. The segment, which is the transport layer data, contains the source port number and the destination port number, and these two are used to identify which socket at the receiving end this packet is going to. So we saw how you create sockets with certain port numbers, either in Java or C. A UDP socket is going to be identified by a two tuple, the destination IP address and the destination port number. When the host receives the UDP segment, it checks the destination port number in the segment and it will direct the segment to the socket with that particular port number. All IP datagrams in UDP with different source IP addresses and different source numbers are still going to the same socket, the same UDP socket. So in UDP there's a one-to-one correspondence between the port number at the receiving end and the socket. In TCP it's not that case. So if you have a UDP connection, the transport layer segment is going to have the source port number and the destination port number. So if you look at this figure, you have two different clients A and B which are connecting to this server. The server has one process running and a single socket running associated with that process. For both clients, the destination port is the same. So when this packet reaches from either client on this end host through the network layer, the transport layer is going to deliver these packets to the same socket. Because this socket, once the network layer has delivered the packet using the IP address of the server, because both of them have the same destination packet or destination port, they are both going to the same socket. So again, a UDP socket, the port number and socket have a one-to-one correspondence on the same host. In a TCP socket, the correspondence is not that simple. TCP uses a 4-tuple. You want the source IP address, the source port number, the destination IP address, and the destination port number. So now look at an example here. You have two clients A and B connecting to the server. The destination port is the same for both the clients in the transport layer segment, but these packets are going to go to different sockets at the server because the sending IP and the sending port are different. So in this example, the sending port is the same for both the clients, but since the IP address, the sender IP address is different, the transport layer at the server will correctly identify the right socket associated with the connection. So in TCP you need 4 values. In UDP, the sender IP and the sender port is not used at all. In TCP you have to use sender IP and sender port to uniquely identify the socket. So for example, in the web server is running at a well-known port, which is 80. If you try to connect to the web server using UDP, all the packets or all the information will go to the same socket. But the way a web server is implemented using either a spawning process or a thread process, once you make the initial connection, you are handed off to a different socket, and the identity of the new socket is made unique by this 4-tuple. Sender port, sender IP address, receiver port, receiver IP address. So in this example, yeah.
Done because TCP wants to have like one-to-one connections between the two sides. I mean, dedicated connections.
Well, TCP is connection oriented. UDP, there is no notion of a connection. Each packet is treated as its own entity. In TCP, you want to maintain some notion of a channel between these two processes. Communication will happen on this channel. So you want to dedicate a socket for this communication. UDP, there is no notion of a connection, so you don't want to dedicate any resources. So in this example, there are different processes associated with each socket. You might have a threaded web server where you have a single process, but you have different threads and different sockets associated with each thread. But the crucial part here is that the sockets are different. The end process might be the same, but there are different sockets for the different connections, the different logical connections. And you use this 4-tuple to do the demultiplexing. Yeah.
So at the last slide,
Yeah.
this where you the two packets coming from the client B, they would both go to the same socket that would UDP.
Yeah.
Just based on the destination.
Just based on the destination.
Dump it into the same packet. But if the fact that it's TCP, then it's going to separate it into the socket.
Yeah.
So for each socket you create a new process. You don't have to.
You see in this example, there's process P4, which has 3 different sockets, so you can use threads. But the demultiplexing is done to sockets. It need not be done to processes. It might be processes, but it's done to the sockets.
And TCP and all, do they all run on as separate processes on their own also? I mean, how does this the whole thing work actually
In the operating system?
I mean, it's software code.
4118. You have to go to an OS class to understand how the internals work. At the network layer, I'm explaining how these different sockets interact with processes. How the different operating systems actually implement that, that's a whole different course. So let's look at what UDP looks like. Well, UDP is the basic extension of IP, the network layer transport used on the internet. So UDP does not provide any guarantees, any services above what the network layer provides, apart from multiplexing and demultiplexing. So it does the basic job which is required for a transport protocol is take the packets and deliver them to the right socket, and take packets from sockets and deliver them to the network layer. Nothing else. It's connectionless, there is no handshaking. Each UDP segment is handled independently of the others. Since there is no flow control or congestion control, UDP can transmit as fast as desired. Now desired may not be the right term here, because if you transmit really fast, you're going to cause problems at the end system or at the network. But sometimes it is useful because no congestion control mechanism is perfect. Sometimes you get wrong signals from the network which you want to ignore, and sometimes you can overcome the effects of congestion control or the effects of congestion at the application layer. So what does congestion control do? It tries to minimize congestion in the network. It's trying to prevent problems here. And so problems that congestion causes are delay and loss. So the philosophy behind some UDP applications is that I'm going to ignore congestion, and I'm going to ignore what congestion might cause in my stream of information transfer. And whatever problems that occur, I'll try to correct it at the application layer. Yeah.
So because UDP doesn't have congestion control, can packets get lost because of that? Like it's not, the queue's not big enough to.
Yeah. So even in TCP, packets will get lost, but TCP has a mechanism to recover those lost packets, and we'll look at that in detail in the next couple of lectures. So what does a UDP PDU look like? Well, we definitely need the source port and the destination port for demultiplexing. Source port is not really needed for demultiplexing. You just need the destination port. But the source port provides kind of a return address at the receiver end. So if the receiver wants to communicate with the sender, the source port tells the receiver which socket it's coming from, and it might be able to communicate. These two fields, length and checksum, add some notion of reliability to UDP. So the length will tell you how many bytes of the application data is going to come in this packet. So if the length of the application data doesn't match the length which is specified in the protocol data unit, then you know that there's something wrong. So the receiver can at least figure out that something went wrong. Similarly, checksum is a way to check if all the bits that this packet carried are right or not. How does checksum work? Well, the goal of checksum is to detect errors like flip bits in transmitted segment. All the packets that are going finally are going over some physical layer. In the physical layer, the bits are being transmitted by using some sort of modulation scheme, and those schemes are susceptible to noise. So you might be sending a 1 on the physical link, but at the receiving end you might receive a 0. Or the router might have some memory problems and it can flip bits. So this checksum will detect this flipping of bits. So the way the checksum works is it will treat the segment content as a sequence of 16-bit integers. So the entire data that's being carried by this UDP packet, you break it up into 16-bit integers, you add up all of these integers. So one segment might contain 20 such integers. You're going to add up all of them, and then the checksum is the ones complement of this final addition. So what's a ones complement? You take a 0, make it 1, take a 1, make it 0. So anything that you get, you just flip the bits, and that field you're going to put in the checksum part of the data. So again, application data, you break it up into 16-bit units, add all of them up. The final result, you take ones complement, so flip all the bits and put the bits here in the checksum field. What the receiver is going to do is it's going to compute the checksum of the received segment, and it will check if that checksum matches the checksum field or not. So it's doing one more error checking beyond the length field. You might receive the right number of bytes or bits, but those bytes or bits might get flipped. There's one point to note about the internet checksum. When you're adding these 16 bits, if there's an overflow in the final bit, that carryover is wrapped around. So that's the only thing to note. I mean, whenever you add to 16-bit numbers, there is this possibility of an overflow occurring at the last bit. So whenever there's a carry, it's wrapped around to the answer. So in this example, suppose your first two 16-bit integers in the data part of the segment look like this, and when you add 0 and 1, you're going to get a 1. But in the final sum, you add that 1, you wrap it around and compute the new sum. And once you have done with all the 16-bit integers that comprise your data segment, then if this is the final sum, the ones complement is just the negative or the flipping of each individual bit. Yeah.
The transfer layer doesn't do anything with this, so if you're going to check the line and the checksum is going to application.
No, the transfer layer is doing it. This is UDP that's doing it.
So UDP includes it in the packet, but when you receive it in the end,
Yeah.
it checks the checksum.
It does the checksum.
Or it just tells you about
It tells you that there's an error. So then the application can decide.
Or you'll still be able to get the wrong package if you want.
Yeah. So what the application is going to do is it's going to at the receiving end, the transport layer will compute the checksum, and it's going to add the checksum with the checksum field. Because the checksum is a ones complement of the checksum of the sum of the original data segment, At the receiving end, the check that you have to do is very simple. You take the checksum field, add it to the checksum that you have obtained. If it's not all ones, that means there's an error. Because you should have obtained this, and the checksum field is the ones complement. Every bit of the final addition should be 1. If it's not 1, then there's an error, and you know that that packet is corrupt.
Just a side question. Like, is it easier to add all 16, all the M units together, or is it better to add pairwise and then?
So there are algorithms and techniques which speed up this process in hardware. That's why 16 bits are used, and checksumming is very fast. It's implemented really fast in hardware and software. Next lecture we'll start with reliability, flow control, and congestion control.